Hello, everyone. My name is Dr. Sean McBride from Marshall University Physics Department. I'd really like to thank Marshall University and the College of Science and the Physics Departments for supporting all of the events that SPS does here, including events like this one. We really appreciate all the help and support that they give us. I'd like to really thank all of them, including the American Institute of Physics. They're helping to financially support this speaker series, as well as our own local chapter of SPS, sponsoring these series of talks, which will go into the spring semester as well. So if you do have an interest in physics, you can check out our Marshall University Physics page. It's www.marshall.edu/physics, and from there you can get to our SPS page as well. So Marshall University is a small R2 institution. There's only about 135 of those in the country. We do have a bachelor's and a master's program. If you're interested, we have 5 areas of emphasis in physics, as well as a master's degree program. So if you're interested in a school of around 12 to 13,000 students, that's an R2 research-focused institution, as well as a focus on teaching physics and other programs, please shoot me an email. And again, I want to thank Ellie White and Jackie Sizemore for doing a wonderful job in putting this together. They've done a really fantastic job. So with that, I'm going to turn it over to Ellie White.
Thank you very much. Really glad to be doing this. So this is an exciting new thing. So yes, I think this is going to be really fun. I'm really looking forward to getting started here. So we're going to start today with a presentation by our wonderful speaker, Dr. Natalia Lewandowska, who I will be very happy to introduce here in just a moment. But after the presentation, we'll actually have time for Q&A. And we hope that you'll share your questions via the YouTube live chat, or you can share your questions on Twitter by tagging our handle, which is @MUPhysicsClub. So if you enjoy this talk, we hope that you will join us for future speakers in the series. We'll be joined by Karen Perez at 7 p.m. on December 1st for a talk on search for ET, and by Dr. Abel Mendez at 7 p.m. on February 16th for a talk on habitable worlds. Many more speakers will be announced soon as well, covering a variety of topics within physics, and we're really excited about them too. So if you'd like to receive email updates about upcoming events, there's a link that's in the video description where you can go and fill out a form to give us your email so that we can keep you up to date. So now it's my honor to introduce my dear friend, astrophysicist Dr. Natalia Lewandowska. Natalia is a multi-wavelength astronomer and currently works as a visiting assistant professor of physics and astronomy at Haverford College in Pennsylvania. And she's previously worked for West Virginia University and the Green Bank Observatory that's also here in West Virginia. She collaborates with scientists around the world to study very fast rotating neutron stars known as pulsars, which she's going to tell us about tonight. And one of her current projects focuses on the Neutron Star Interior Composition Explorer, or NICER mission, which is an instrument mounted on the International Space Station that was constructed solely for the observations of neutron stars. Natalia is also a member of the Equity and Inclusion Working Group of the International Astronomical Union, and is currently the group leader of the Neurodiversity and Mental Health Sub-Working Group to make the field of astronomy and astrophysics more accessible to all. So I'm very excited to turn things over to her right now so we can get started. So thanks again to all of you for coming, and especially to you, Natalia, for making time to join us today to teach us about these mysterious clocks in the sky.
Thank you. I need sharing permission from you. Yes, now it's working. Okay. Thank you very much, Ellie. So welcome, everyone. Thank you so much for giving me the opportunity to talk about my research here and today. It's an honor to kind of like talk to the Marshall faculty, students, and also staff members. So I wish I could be there in person to give this talk in front of you. Unfortunately, COVID prevents that, but hey, at least we can talk virtually, which is pretty safe for all of us. So as Ellie already pointed out, I'm currently a visiting assistant professor of physics and astronomy at Haverford College in Pennsylvania. And I do study, and I have been studying for the last pretty much 10 years, stars that are also called perfect clocks in the sky. And this is what I would like to talk to you a little bit about today. So as Ellie already pointed out, I started my career in radio astronomy at the Green Bank Observatory, where I worked from 2016 to 2018. It's a beautiful place in West Virginia. You see it here, hopefully indicated with this little star in Pocahontas County. And that's the Green Bank Telescope, the largest fully steerable radio telescope currently on Earth. So the Green Bank Observatory is a very famous place due to many reasons, and hopefully I will be able to explain some of them today. And working there was a very unique experience to me. And thankfully, I also met Ellie on the way. So she was visiting the Green Bank Observatory during one summer, and I was working there. So we started talking. And I remember our first encounter very well because I was giving a colloquium at the Green Bank Observatory, and she was the only female scientist sitting in the audience. So this is definitely an eye catcher when you usually think you are the only woman in the room, but then you are actually not the only woman in the room. So that was pretty cool. So anyways, if you actually ever get the opportunity outside of these crazy pandemic times right now to go to the Green Bank Observatory, you should definitely go. It's a very, very different place, but it's definitely worthwhile visiting. I should add that your mobile phones will not be working there because for those of you who don't know, Green Bank is located in an area which is indicated here on this map. This is the so-called National Radio Quiet Zone. It's a zone that was set by law as no Wi-Fi, no mobile phone, no anything that causes something that we refer to as radio frequency interference. So that's the reason why your mobile phones will not work in roundabout a radius of 1 hour drive around the observatory, but you will get used to it. So after my time at the Green Bank Observatory, I became a postdoc at West Virginia University, which is also an equally famous place. So just to show you, I moved basically from here up here in a northern part of West Virginia. So West Virginia University is an R1 institute. It's very focused, it's very research focused and a very good place to study pulsars. So if you are ever interested in maybe also applying there for your PhD, for instance, just let me know. And after that, and just recently, I moved to Pennsylvania. So I just kind of like, this is a little bit small, but I hope you can see it anyway. So West Virginia University is here and Haverford is here. So I made quite a jump, I noticed, with this move. So I'm not living in West Virginia anymore, which is kind of like a little bit odd, but Pennsylvania is equally nice and the people are super friendly. And that's actually one of the main buildings, the oldest buildings at Haverford College, which is located in Haverford nearby, so in the outskirts of Philadelphia. Okay, but enough about me. I would just add like one sentence that usually you will find me either on the top of a telescope, as you see on the photo on the poster. I'm standing at the top of the Arecibo radio telescope there in Puerto Rico, or you will find me somewhere in a very remote place, like on a mountain where you have optical telescopes. So long story short, I am something that we refer to as observational astronomer. So I do observe various objects in space, but mostly I focus on stars. And today I would like to give you a short overview what we actually have in the universe, like which objects and what do we know about them. So obviously we have like lots of galaxies when we go from large scales to smaller scales. Our actually galaxy, the Milky Way, has a very similar shape, so a kind of like spiral form. Then we also have smaller galaxies like the Large Magellanic Cloud with lots of nebulae and gases in there and star-forming regions. Then when we go over to the star-forming regions, we see like very dense clusters of stars and still dust. So these dark patches are actually dust clouds through which we cannot see through with an optical telescope. And the bluish areas here are actually reflections from these young stars that were just born. with just born, I usually say they are a couple of thousands of years old, because stars have very much different lifetimes than people do. And then obviously we also have the solar system, which you see here. So we are located here on Earth. And I know that some of you who are maybe my age or a little bit older notice that Pluto is not there. That's right, because Pluto was designated as a, some people say degraded, but I would say designated as a dwarf planet a couple of years ago by the International Astronomical Union. So we have lots of interesting objects in space. We also have comets. This is actually, yeah, this is Hale-Bopp. This was a comet which was visible in 1996. It came very near to Earth, so we could observe it even with small telescopes. And you see it has kind of like a dust tail, the wider one, and even a gas tail, which is the bluish part. So comets are very frequent visitors of the solar system. And then we also have something that we refer to as asteroids. Maybe some of you know that there is kind of like an asteroid belt between Mars and Jupiter. And sometimes it happens that if Jupiter kind of like grabs one of them via its gravity, that some of them might also turn in our direction and kind of like visit the planet, hopefully without a collision. So as I indicated earlier, I do study stars, and every star is being born in a nebula or in a dust cloud. We also call them molecular clouds. So one of those areas you see here, this is the so-called Eagle Nebula. Or M16 when you take the catalog name. And this photo was taken with the Hubble Space Telescope, an instrument that we are super grateful for because it provides like not only pretty pictures, but also lots of different knowledge at optical wavelengths and also partially infrared. So what you see here is kind of like lots of dust, right? And you see that something emits these parts of the nebula, which are a little bit farther away. And this whole picture indicates that behind this core here, there are new stars that were just born like recently. And we cannot see them because the wind of that star has not blown like all of the dust away yet. But it's definitely there because it's illuminating the background kind of like of this nebula. So stars are born in such molecular clouds or in dust clouds. But stars can also die. And when a star dies, there are several outcomes how this death can look like. So when we have, let's take it from the top, when we have like a low to average mass star like the sun, this sun will at some point become like a bigger star. We call this a red giant. And then it will end up in a much smaller star, which we refer to as white dwarf. And a white dwarf is just a very, very small star. It has the size of the Earth, and it's not doing nuclear fusion in its interior. So it's not converting hydrogen to helium anymore. It consists completely of carbon, and that's what our sun also will become in many billion, kind of like million years from now on. So no worries, this will not happen tomorrow. Then when we have like a large mass star like this one, the outcome can be a little bit different. And I will explain the details in a moment how it comes to that. This large mass star can become also a red giant star, but it is a little bit bigger when you compare this one with that one. And then the end product can be a neutron star. And this is actually what I do study, neutron stars. And we will come back to them in a moment. And then the last scenario, which is an outcome that I'm certain many of you have already heard about, is when you have a very large mass star that also becomes a red giant at some point and ends up in a black hole. So long story short, if you are asking yourself, okay, but how big are the differences, in masses? So we assume, based on our computer simulations, that this scenario happens when you have a star that is at least 8 times the mass of our sun, so bigger. And this scenario happens when we have like a star, we call this progenitor star, of at least 20 times the mass of the sun. So it must be like super heavy. So just to describe a little bit the scenarios which we have for the death of a star. Okay, before I come to that, let me just emphasize that on the way here to a neutron star as well as a black hole, something else happens, which we refer to as a supernova. And what this is, I will show you hopefully in this short movie. Yeah, lots of tragic music included. I did not make this movie, but I really like it. So this is a so-called supernova explosion. So it happens when a star explodes, and dying stars, dependent, on their initial mass, can actually explode. So this takes place basically where this arrow is before the neutron star forms, and also equally here before the black hole forms. So every time we speak about a supernova, we are talking about a star that does not like explode into small pieces, but it blows off all of its outer shells. And that's what you just saw in this short movie. So the specific kind of supernova that produces a neutron star is called core collapse. And this picture looks quite like an onion, right? And because we think about an onion structure when we talk about stars, and think about, okay, what makes a star stable? So a star is converting hydrogen to helium in its core at the beginning. And this gas pressure, which is produced by this process, kind of like acts in an opposite direction to the gravitational pressure, which acts on the star based on its mass. So a star is stable as long as these two forces are equal, in size. But at some point when the star burns up the hydrogen, which you see here in this outer shell, this gas pressure becomes like less and less. So the gravitational pressure takes over and starts contracting the star. But it can contract the star only to a certain extent until this explosion, which we refer to as supernova, takes place. And then after the star has kind of like kicked off all of its outer layers, you have like these beautiful nebulae, which we refer to as supernova remnants. So that's the Crab Nebula. It is also like the central part of the nebula that you just saw in the movie. Then we have a couple of other examples here. And interestingly, all of them look quite a little bit different, which means that all of these supernova explosions happen in a slightly different way, following the same chain of physics that we already know about, but producing like different examples of remnants. And one remnant that I'm working with a lot is actually the Crab Nebula remnant. It's in here, and in here you see like a dot, and that's the neutron star, an object that we also call Crab Pulsar. So such a supernova remnant, a neutron star, is actually a very exotic object. That's not a photo, that's just a sketch made by one of the members of NASA. But what we see here is actually a very small star, and these lines here are magnetic field lines. And to explain this picture, I will go a little bit into the characteristics of a neutron star. So a neutron star is nothing more than the collapsed core of a massive star. It has roughly the size of a city. So if you would look at Manhattan, as is shown in this picture, it would have like the size in terms of diameter of Manhattan. It has, though, the mass of approximately 1.4 solar masses. And the reason, and the resulting reason out of that, is that the density is super high. So imagine you have a star that has more mass than the sun, and it's kind of like contracted to a very small size, which has the size of a city, which means that when you take like just a tablespoon full of neutron star mass, it would be heavier. I mean, it would be 1 billion times heavier than normal mass, let's say the mass of the sun. So a neutron star is a very kind of like exotic object because it's very small, it's very massive, and it's very dense. And we know already more than 2,500 of them. We don't really know yet how the interior of a neutron star looks like, so the exact composition is not known. But we assume that each neutron star has a core, something that we call neutron superfluid, so a non-solid area, a solid crust, the first part with free electrons, and a crystalline outer crust. How do we know this? Because we have been observing neutron stars for more than 50 years by now, and we actually drew some observations out of that kind of like help us to determine what a neutron star might be comprised of. So these values here, these density values, are actually just the results of simulations, because when we scientists try to understand something, we compare observations with simulations. So you can start either with observing an object and then building a theoretical model, or you can start building the theoretical model and then adjusting it to your observations. So there are many different ways how one can do that. And how did this start? Actually, all of this started a little bit over 50 years ago by now in Cambridge in the UK. So this young lady here, Jocelyn Bell Burnell, was a grad student back then, and she actually discovered just by accident the very first neutron star, which is depicted here as CP 1919 in these very old flowchart diagrams that she took back then. So she was actually observing like quasars, which are very far, very distant galaxies, with a radio telescope that she built on her own. This was a part of her PhD thesis. And while she was observing these very distant galaxies, she also noticed that this little piece of scruff, as she called it, showed up on a regular basis in her data. So this caught her attention because she had, I mean, I'm not kidding, she had miles of flowchart recordings coming out of these observations. So she kind of like, when she looked at those, she noticed everything that was a little bit different from what she expected. And this little piece of scruff was one of these things. So then she took chart recorder with a higher time resolution and kind of like reobserved this source and detected pulsations that you see here. So very regular pulses from a source. And at first people thought, are these little green men? So they labeled this detection LGM. But no, it were not like aliens or extraterrestrials. This was actually a signal from a star. And this is just a photo of the original chart recording that led to the detection of the very first neutron star. It turned out that this neutron star, it's these days called B1919 plus 21. So these are just the coordinates, and PSR is standing for pulsar. It's a very normal neutron star in the constellation of Vulpecula, and it has a rotation period of 1.3 seconds, roughly. So this is what we these days refer to as a slow pulsar, but this young lady actually started the whole branch of neutron star studies that thousands of people are working on today. So what is actually a neutron star? So there are many neutron stars, but not all of them are pulsars. I'm actually only working on pulsars at the moment. And a pulsar is nothing more than a very fast rotating neutron star, which is very highly magnetized. And you see that it emits beams of emission here. So this would be the radio emission, which we detect from it. And every time one of these beams crosses our line of sight, we see a pulse in the following way. So it basically works like a lighthouse. That's the reason why we call pulsars also lighthouses. But that's what a pulsar is. So we see this pulse from this kind of star just because one of these beams crosses our line of sight. And let me just very, very briefly kind of like tell you a little bit about the properties of pulsars. So pulsars have been detected. I told you we know we know more than 2,500 by now. They have like rotation periods which are in this range, basically very, very fast ones to very, very slow ones. So the slowest one has actually a rotation period of 8.2 seconds. So every 8.2 seconds, this beam crosses your line of sight. When you take the inverse values of that, you will actually come to a quantity that we define as rotational frequency. And due to some reason, I really like way more to discuss pulsars in terms of rotational frequencies than rotational periods, because we can actually give you these numbers in units of hertz. And when I say a pulsar has a rotational frequency of 716 hertz, which is the maximum value that we know about so far, I mean with that this beam crosses your line of sight 716 times per second. So that's how fast they are. They are super fast. Their magnetic fields are also very large. I was so free to give you the numbers here. They range from 10 to 11 to 10 to 12 Gauss. When you compare this with the magnetic field on Earth, which is 0.25 Gauss on some places of Earth, this is approximately that much more when you take only the lower limit. So their magnetic fields are much higher than that on Earth. So would you like to fly there? I would say no, because the magnetic field would definitely have an effect on us. But that's the reason why we refer to pulsars as exotic, because they have characteristics that we cannot simulate in any lab here on Earth. We cannot generate such a very strong magnetic field. This is not possible without doing like real damage to our environment. And there are also two main groups of pulsars. We call them ordinary pulsars and recycled pulsars. And if I want to describe this to you, I would use like the following plot, which is here. This is the so-called PPdot diagram. So it's nothing more than taking the period of each pulsar that we know about in seconds and the first derivative of this period and put it on the y-axis and plot both quantities in logarithmic scale against each other. Then you get like these weird shapes. So each dot here is one neutron star, and ordinary pulsars are in this big group here that looks a little bit like North America, actually. And recycled pulsars are in the smaller group here. And as the legend here indicates, some of them are radio loud, so can be observed at radio wavelengths. Some of them, these are the blue dots, some of them are radio and high energy loud, which means they can be observed at radio and or X-rays, optical wavelengths, also other wavelengths than just radio. And some other ones indicated by the pink dots are actually radio quiet, which means we cannot see them at radio wavelengths at all. So we have like a very, very large diversity of neutron stars / pulsars that we know about. But something that I just jumped over a moment ago is actually the fastest pulsar that we currently know about. So this guy has this name. It has a rotational period of 0.0014 seconds or 716 hertz when you take the inverse value. So it is really kind of like showing, or its beam is sweeping through your line of sight like 716 times per second. That's so fast. If we would convert this into kind of like acoustic signals, we would not hear like a difference. We would probably just hear like a hum, like the whole time. And this pulsar is located in a globular cluster that we refer to as Tersan 5. And Tersan 5 is actually a very interesting cluster. You see a photo of it here. And you see that you have lots of stars in there, which are kind of like bluish. Some of them are a little bit yellowish or orange. So it has kind of like an accumulation of more than 1,000 stars, which are actually kind of like all in a very tight place together. That's the reason why we call this globular cluster and not open cluster. And many pulsars have been discovered in such globular clusters, which is a very interesting place for them to form, because remember, each of them forms out of a supernova explosion. So a very violent kind of explosion. And the globular cluster still survives that. So that's amazing. Okay, so I said a moment ago that if you would convert the signals from a pulsar into sounds, that you could actually hear it, right? So here I have now 3 examples. So this pulsar has a rotational frequency of 1.4 hertz. It's called BO329 plus 54. And I would like to just show you this very slow pulsar, as we call it. So imagine that this beam crosses your line of sight once 1.4 times every second. So here we go. Okay, it sounded like it had a hiccup like towards the end, but I believe it's a very stable object. So this is when you hear, when you basically convert the radio signals from a pulsar into sounds and want to listen to it. So this is a slow pulsar. My second example is one of my favorite objects. It's the Crab pulsar, or BO531 plus 21, and it has a rotational frequency of 30 hertz. So this will sound a little bit different. Stay tuned. This is a little bit too much for the ears, I know, but it sounds a little bit like a broken washing machine, I was once told by one of my students. So imagine this time you hear the beam crossing your line of sight 30 times per second. So 30 hertz. And then my last example is the one of a very fast pulsar. Actually, this one, B1937 plus 21, was discovered in 1982, and it was the very first millisecond pulsar discovered. So this one has a rotational frequency of 641 hertz. It's the second fastest pulsar apart from the one that I mentioned earlier. And when you convert its data into sounds, you will hear the following. So see, you cannot, our ears cannot really hear the different beams anymore. So it's not like we hear a tick, tick, tick. The ticks are coming at such a high frequency that our ears are not able to kind of like discern them anymore. And if you would have like this other pulsar with 716 hertz rotational frequency, it would be even worse. So you would probably only hear a hum. So pulsars can be super, super fast, and they kind of like range from a very low values when we have like rotational frequencies or rotational frequencies from 8.2 seconds. So you hear the beam every kind of like 8.2 seconds, or until 716 hertz. One of my favorite objects that I would like to talk about more today is the Crab Nebula and its pulsar. So this whole nebula here, also called M1, so Messier 1, is a supernova remnant that was born approximately 1,000 years ago. And as you can see, I mean, I don't know why it was really called the Crab Nebula, probably because the person who observed it for the first time saw somehow the shape of a crab in it, but I don't know. I mean, I don't really see the shape of a crab. So But okay, the name sticks. So this nebula is super, super special because it was observed way before the neutron star that it's inside here was discovered in it to be more bright than it should be. I mean, it was discovered, I don't know the exact year, somewhere in the 1900s. 19th century, that is. And people noticed, like in subsequent observations, that it was brighter than it was supposed to be. And they kind of like asked the favorite question of every physicist, why? And so they kept observing it. And as you can see with time, these are more newer pictures. We can observe it at radio, at infrared, at optical wavelengths, ultraviolet, and also X-rays. And when you take all of these pictures and look at them separately, you see that each of them has a different shape. Because with every different wavelength that we observe this object at, we see something different. And this whole picture here is just kind of like the overlap of all of them. That's the reason why you see so many colors in here. And these structures here, which we refer to as filaments, are actually the former outer layers of the star that exploded in a supernova explosion. And then you see also this kind of like torus-like structure here. This is actually the part of the nebula that the pulsar is powering. We say that the pulsar is kind of like powering the nebula. And I will come to this in a moment about this kind of like powering mechanism. So this nebula kind of like started to exist approximately 1,000 years ago. And we know this because in 1054 AD, people actually observed the supernova explosion, and they either wrote it down like Chinese astronomers, or they made pictographs like Native Americans. And this one is located in Chaco Canyon in New Mexico, and you can still visit it today. So what they actually saw during the day was not only the moon, and you can sometimes see the moon during the day, right? They also saw an additional star. So imagine you have like a very beautiful day, blue skies, and you don't only see the sun, but like an additional star. And this was light from this supernova explosion that created the Crab Nebula that had reached us. And people saw this and wrote it down or made these pictographs. So that's how we know that they saw this explosion. And when the Crab pulsar was discovered in this nebula, this was kind of like the proof, like, okay, a neutron star is really being born out of a supernova explosion. This was kind of like a hypothesis back then. It was not proven yet, but with the Crab Nebula, it became kind of like solid proof. Okay, so the Crab pulsar, this little star that you see in here, was discovered in 1968, actually at the Green Bank Observatory. What we know about it now is that it has a rotational period of 33 milliseconds or rotational frequency of 30 hertz. And I just said a moment ago that it was discovered, well, maybe I did not say it, but I just talked about it. It was discovered at radio wavelengths originally, so with a radio telescope. But when you look at this short movie here, you see this is not a radio image. This is actually a series of X-ray images taken with the Chandra satellite and overlapped. And this is what I meant a moment ago with the pulsar is powering the nebula, because look at all of these pulsations that are happening here. So the pulsar is sending all of its energy also into the nebula. And this is what we mean when we say it's powering the nebula or its supernova remnant. So that's actually why we call this whole complex also Crab Nebula complex, and not only pulsar or nebula. This number here, 58 hertz, is actually was determined by a group of scientists from the Jodrell Bank Observatory in the UK, and it was published under Line et al. In 2015. And it basically showed a way to calculate the rotational frequency of the Crab pulsar at the time when it was born. So these guys used very unique data sets, 45 years of radio data of the Crab pulsar only, and they managed to kind of like calculate the rotational frequency of the Crab pulsar at the time when it was born out of that. It is a very interesting study. So if you want, I'm happy to send you the link to this publication. So what this means is when you compare 58 Hertz 1,000 years ago and 30 Hertz now, this means that the Crab pulsar is slowing down. And it's not only the Crab, actually every pulsar is slowing down with time, because when they kind of like rotate and their beams sweep through your line of sight, they are kind of like emitting their energy into space, but they are not getting it back from anywhere. So this means they slow down with time. And this is the difference that you see also in the case of the Crab pulsar here. Okay, so I indicated already this X-ray image from the Crab pulsar. And the Crab is a very fascinating pulsar due to many reasons. But one of the many reasons is that we see its emission, which usually shows itself as a bright peak, which we refer to as the main pulse, and as a not so bright peak, which we call the interpulse. And these are two rotations. That's what you see here, the interpulse twice. But let's take only one rotation. So let's look at only this part of the picture. So we see this double peak structure, not only at radio, but also at optical wavelengths, X-rays, hard X-rays, and all different fields of gamma rays. So long story short, we actually see the pulsed emission from the Crab pulsar throughout large parts of the electromagnetic spectrum. So it's not radio quiet, for instance, as I indicated in this PPdot diagram. It's actually very, very loud. And till today, we have no idea how it's generating its emission, which is also one of my fields of study. As I already said, the Crab pulsar was detected with a telescope that doesn't exist anymore, but it did for a very long time, the 300-foot telescope at the Green Bank Observatory. And this discovery was made, well, when you compare 1967 with 68, shortly after the discovery of the very first neutron star by Jocelyn Bell Burnell. And the detection of the Crab pulsar was a very interesting one because it was not detected via its periodic emission. Actually, it was detected by a not periodic form of its emission. And this is kind of like one plot out of this detection paper. And what you see here are pulses that are not straight but slanted because they travel through the interstellar medium and go and experience an effect that we call dispersion. But some of these pulses are super bright, like this one. And these very bright single pulses, so what I mean with single pulse is, let me just take my little pulsar model here. Usually, when you want to see the signal from a pulsar, you need to add many, many of these rotations up to increase the signal to noise ratio. But when I say, oh, I mean single pulses, and I literally mean just one rotation of the pulsar. So I hope this clarifies what I mean with a single pulse. And normally these single pulses are not bright enough to be detected just like that. But in the case of the Crab, they were. And they have a longer story behind them. But when you look at single radio pulses from the Crab, and that's actually a plot from my PhD thesis, you see the main pulse, which is nice and bright. Every single line here that I stacked together is one rotation of the Crab pulsar. So, but apart from this very bright main pulse, you also see lots of stuff in between. So single pulses kind of like when they travel through the interstellar medium, which is the space between us and the star, they kind of like are a little bit distorted and, you know, kind of like have various forms of distortions, which kind of like makes them a little bit hard to study, but also explains why we cannot always see them just like that. But in the case of the Crab, the story is a little bit different. So that's actually radio data that I'm just about to show you, taken with the Lowell telescope, which is one of the biggest telescopes at the Jodrell Bank Observatory in the UK. And you will see something that I refer to as noise level. And I would like to ask you to pay your attention to everything that is above that noise level. So here we go. You saw this last one. So this was a very, very bright single pulse. So the Crab has this unique characteristic, or maybe it's not unique anymore, but it's super interesting. It produces single pulses that are so bright, they are at least 1,000 times brighter than other single pulses, and they do not show up during every rotation. Therefore, we call them irregular. So these single pulses that are so bright is what we call radio giant pulses. And the Crab pulsar was originally discovered via its radio giant pulses, so an not periodic form of emission, even though it also shows periodic emission. And these radio giant pulses are a big focus of my current research work. So as you see in this plot here, you have the time given in nanoseconds, so 10 to the power of -9 seconds. And when you look at this very bright radio giant pulse and compare the total intensity in Janskis here, you easily notice it's in the range of about 2 megajanskis. So if you are not a radio astronomer, this will not tell you much what 2 megajanskis mean. But let me just assure you that this means it's very, very bright in comparison with other single pulses. So what we also observed in the case of these very bright single pulses, known as radio giant pulses, is that the shorter they are, the brighter they become. So the shorter they are, the higher is their intensity. And I believe this one here has a width, so a pulse width of approximately 0.4 nanoseconds and an intensity of 2 megajanskis. So this is actually a very interesting object. What we also observed is that they do not show up periodically, as I already said. So they show up every couple of rotations, and sometimes they look like that. Sometimes they show up in groups. Sometimes they are there in very large groups, and sometimes they are solitary again. So each radio giant pulse is kind of like different. But coming back a little bit, and I think I said everything about that already, but you have it on the slides anyways. When we compare the width of such a pulse and its intensity, and we try to convert it to the area that kind of like creates it on the surface of the neutron star. So think back about a pulsar being a neutron star, and then having only a diameter of roughly 6 to 7 miles, or 7.5 miles. And then you think about an emission region on the surface of the neutron star, which has kind of like a diameter of about 60 centimeters. So that's that much. So now you ask yourself, oh man, what is capable of producing such a very bright single pulse from such a small area on this tiny neutron star? So the answer is we still don't know, but this is one topic of my research that we actually want to solve. And I always say I will study the Crab pulsar until I understand it, which might take my whole life, and more of the future, but it's certainly a super interesting object to study. Because what we observed is that these very bright single pulses show up only at the faces, and the phase is a quantity that describes the progression of the rotation of a neutron star or a pulsar. So basically, when the neutron star is still, it's located like that. And when it turns once around, it has the phase of 1. So when it doesn't move, it has the phase of 0. And after one full rotation, it has the phase of 1. So these are just fractional values that we use to describe in which part of its rotation the neutron star currently is. And we observed that radio giant pulses only show up at the phase range of this peak, which is the main pulse, or of that peak, which is the interpulse. Scientists kind of like say they are phase bound, and we don't really know why it's doing it like that, why we don't see radio giant pulses somewhere here or somewhere here or here. There are different theories. But one additional thing that we have tried to find is if we can see radio giant pulses also at other wavelengths than just radio. Because you see the Crab is very active at all of these other wavelengths. So it's a multi-wavelength object, but we did not know in the beginning if we would see radio giant pulses also at other wavelengths. I will come back to this in a sec. And we actually found a correlation a couple of years ago with optical photons. So what does this mean? The people who did the study, they observed the Crab pulsar at radio wavelengths and with an optical telescope simultaneously. So observed the Crab at the same time at both wavelengths, then analyzed the data, found out when the non-periodic radio giant pulses occurred in the radio data, and looked at the optical flux during these rotations when radio giant pulses showed up in the radio data. And they found out that the optical flux indicated by the black curve here is approximately 3% higher when a radio giant pulse occurs, and the radio giant pulse is here, then in comparison with the optical flux, which shows up when no radio giant pulse occurs, and that's the red curve. So this is something what we refer to as a correlation. So what does this mean? It means that radio giant pulses from the Crab have an optical counterpart, which is super interesting because this allows us to kind of like try to track down the physics behind radio giant pulses also from the direction of other wavelengths than just radio, which makes it easier for us. So when we come back to this is kind of like the multi-wavelength picture of the Crab, right? So for a very, very long time, for the first 40 years after we discovered the Crab pulsar, we did not know that at radio wavelengths, so only looking at this window, it has a way more complex phase than just these two peaks that we see here. Because when you go to kind of like only radio observations of the Crab and go from 0.4 gigahertz to 28 gigahertz, you do not see only 1 or 2 emission components, you actually see 7. And now think back about the short movie that I showed you at the very beginning in which the beam crosses your line of sight. So this was just one peak, and here you have 7. So how would you imagine that you need to kind of like change this short movie to fit this observation? And I know that's a very mean question because I don't have an answer for this either. It just shows us that nature is way more complex than our models, and we still need to work on or do a very good job on kind of like adjusting our theoretical models to our observations. So the Crab is also unique because it shows that many emission components at radio, and we have still no idea how it's doing that. And some of the open questions that I have and many other of my colleagues have is, what is the emission mechanism behind radio giant pulses? Because they are so extreme, because they are so short in duration and width, because they are so bright, how does a pulsar do that? So we try to track down the region of origin in the magnetosphere, and the magnetosphere is basically the atmosphere of a pulsar that is co-rotating. It's within these closed magnetic field lines here, so that's just a sketch. And we try to find a so-called multi-wavelength component of giant pulses, as we managed already to do with the optical correlation that we found, but we are also looking farther. We are also looking at different parts of the electromagnetic spectrum, because we also want to understand, and these are all open questions here, so I do not have like super big answers for all of them. We also want to understand if the Crab pulsar is also unique, or if it's just one part of a special group of pulsars, because only a handful of pulsars show these radio giant pulses, and we have no idea why. So when we go back to this PPdot diagram, that's a slightly different version that you just saw before, but you recognize like the ordinary group of pulsars here and recycled or millisecond pulsars here. The Crab is actually here. So I indicated it in this PPdot diagram. And it's a very special place because all young pulsars, and with young, we really mean like 1,000 years old, they actually show up roundabout in this area of the PPdot diagram. And then when they age, they actually move over in this group here. So the Crab is still a very young object. And remember, it has like radio giant pulses. And for many years, we thought that radio giant pulses are a characteristic of young pulsars. But this doesn't seem to be the case. Because in the meantime, we also found like more pulsars that were reported to be giant pulse emitters. That's how we call them. And you see that some of them are located in this group, so they are older than the Crab, but others are located in this group. And millisecond pulsars or recycled pulsars are actually much older than the pulsars located in this group. Why? We call them recycled pulsars because, as every pulsar, they were born in a supernova explosion, but they also aged, they became very slow, and then due to the accretion of mass from actually, let's say, binary companion, so another star, they managed to spin up and to get recycled and basically be visible again. So that's just in a nutshell why we call them recycled pulsars. And giant pulsars have been also observed in the case of recycled pulsars. So it's not kind of like a characteristics of young pulsars only, because recycled pulsars are old. They are very old, but they are also very stable. So what does connect all of these pulsars, you know, with their giant pulse emission is still a very large area to explore. So what I've been working on recently, just to give you an outline, is actually the giant pulse emission, not only from the Crab, but also from millisecond pulsars, so from these recycled pulsars. And one object that I do study quite a lot is actually this one here, B1937 plus 21. If you remember, I showed you like the kind of like sounds from one of them. This was the one in which case you could not kind of like differentiate between the beams crossing through your line of sight. It just sounded like one continuous sound. And another one which has this name, it's B1821 plus 24A. It's actually the first recycled pulsar that was discovered in a globular cluster. So let me just go very quickly, because my time is short today, into detail about this guy. So B1937 is super interesting, not only because it was the very first millisecond pulsar discovered, not because it's also so fast, but because it shows radio giant pulses. And in comparison with the Crab, it's very old. So these two could be not more different from each other in their evolution histories, but they are still similar regarding radio giant pulses. And the question is why? So in 2003, an interesting publication came out in which people observed like the radio emission from B1937. And same as in the case of the Crab, you see a bright pulse, which is the main pulse. And you see a second pulse, which we refer to as interpulse. And the interesting part of that study was that they also simultaneously observed B1937 at X-rays, which are shown here in the two upper parts of this figure. And they saw that the radio giant pulses from B1937 are much better aligned in pulse phase with the X-ray emission than the regular radio emission. And this is super interesting because we have not observed this in such detail in any other case of a pulsar yet. So what does this mean? This means that the pulsar is generating its radio giant pulse emission and its X-ray emission probably in the same area in its magnetosphere. And now the question is where? Where is it happening? So that's the reason why in 2017, I decided to join the NICER collaboration. As Ellie already indicated, NICER is the Neutron Star Interior Composition Explorer. It's an instrument that you might or might not see here on the ISS. It's actually here where my cursor is. So it's this little box. It's actually a little bit bigger than the washing machine, but it's mounted on the ISS, on the International Space Station. And the special thing about it is that it was designed only for the observation of neutron stars, not only pulsars, but all kinds of neutron stars. And as this indicates, I don't have any time to go into detail about this, but there are more neutron stars than pulsars. So pulsars are not the only kind of neutron stars that we know about. But anyways, this instrument observes in the so-called soft X-ray range. It was launched in 2017. It has been operational since 2017. Its mission lifetime was at the beginning supposed to be 18 months, but it produces such good results that we kind of like extended its lifetime already twice, because it still produces very, very good data of all kinds of neutron stars. Oh yeah, and here is kind of like nicer. So it's really just one little box on this gigantic ISS, but it's fully operational. And the reason why we mounted it on the ISS was that that way we would not need to bring it into an orbit, and it would be kind of like a very money-saving procedure to just have it on the International Space Station. Okay, so there are many open questions that my research tries to answer, and not only my research field, but it's also the research field of many others. So I'm usually asking myself if there are any other differences between ordinary and millisecond or recycled pulsars, if these giant pulses that we kind of like detect from the Crab pulsar, if they are unique or if they are just normal. So I'm trying to compare their characteristics with the ones of B1937, for instance. So are there different kinds of radio giant pulses? If you think back about this PPdot diagram, there might be. Or if this is all just bogus, or they all have like a common emission mechanism. So these are all questions that I still do have. But let me come to the summary now. I hope I could give you like an exciting overview of what I'm working on and what pulsars are actually about. So just to summarize, a neutron star is nothing more than the collapsed core of a massive star. We say collapsed because think back about the scenario when the gas pressure from the inside is not strong enough to hold up the gravitational pressure from the outside. When this happens, the star is being contracted. So it kind of like collapses into its core. A neutron star is something that we refer to as a stellar corpse. That sounds weird, but it really is like that. It is the final stage of stellar evolution. Not much happens after that. It is so far the smallest and most compact stellar object that we know about. I mean, think back about these numbers, the magnetic field that is so much stronger than here on Earth, star kind of like with the mass of 1.4 suns, kind of like squeezed into a little star that has kind of like the diameter of 6 to 7.5 miles. So it's kind of like a very exotic object in terms of physics. And a pulsar is just one very special kind of neutron star. So we know more neutron stars than pulsars. In the case of a pulsar, you have a very fast rotating and highly magnetized neutron star that emits these periodic pulses. But these periodic pulses are not generated because the star is really pulsating. We also know pulsating stars, and that's a different scenario. They show up because their beams cross our line of sight, same as in the case of a lighthouse. So think back about that scenario when you think about pulsars. And yeah, I think with that, I'm at the end of my presentation. So thank you very much. Thanks, Ellie.
Thank you so much, Natalia. That was super. I really enjoyed that. I know I learned some things.
Cool.
So thank you so much. I think Jackie is going to lead us in any questions that people have.
Yeah, thank you very much, Dr. Lewandowska. That was very well done.
Thank you.
Yeah, so if you guys want to ask some questions for Dr. Lewandowska, you can enter them into the chat on YouTube, or you can tweet at Society. What is the Twitter handle, Ellie?
Yeah, it's at MU Physics Club.
MU Physics.
MU Physics
Club. Okay, great. So while you guys are typing out your questions, I just want to plug really quick. So we are having a fundraiser for doing these talks right now. We're giving all of our presenters honoraria. If you would like to support these talks, what you can do is you can donate to SPS, Society of Physics Students, and we'll enter you for a chance to win a Yeti cooler. Not sure when you get to use the Yeti cooler. Maybe you want to have like a camp out in your backyard or something during our next lockdown. But yeah, if you guys want to donate, and I will submit this to the chat too, but you can email me at sizemore85@marshall.edu. So if you're interested, you can donate, I think it's $5 for one ticket or $10 for 3 tickets for entering for your chance to win. Okay, so with that, we'll get to some questions. Thank you to all of you who were commenting during the stream. Apostolos commented earlier, I think when we were talking about the periods of the pulsars, he said, I'll add that pulsar J0250 plus 5854 has actually recently extended the record to 23.5 seconds. That's
awesome.
Cool.
That's really cool.
So again, from Apostolos, the first question here, he says, are you aware of any other multi-wavelength GP correlation besides the radio-optical example you showed? And a follow-up question, what about centimeter-millimeter wavelength correlations?
So I'm aware of one, but I'm not allowed to talk about it yet because the paper has not been accepted yet. But stay tuned. In the next couple of months, there will be one more result in this case. So I don't know if you are familiar with this telescope, but the Atacama Large Millimeter Array in Chile is actually an interferometer that does not only observe at higher radio wavelengths, but also at infrared. So we are actually preparing a proposal, kind of like a huge group of people, different collaborators from all around the world, to submit this proposal in April next year to ask for simultaneous observations of the Crab pulsar with ALMA and with several other facilities. So we will do a huge, hopefully when we get the time, we will do a huge multi-wavelength study, which actually takes a lot of work in terms of coordination, but it's also a lot of fun because, you know, all of these observations are not cheap to carry out. And when you observe like one object with several telescopes, you kind of can get more information out of that than just with one. So we are about to move into this area next year, hopefully.
Great, thank you. Ash wants to know, I'm curious to know if a dying star can create something smaller than a white dwarf.
That's an interesting question. And the answer is no, because you have something like electron degeneracy pressure. So similar as in the case of a neutron star, when we have like a star that will become a white dwarf, it also burns kind of like, it converts hydrogen to helium and then helium to carbon. And to make the switch between all of these elements, you need to have higher temperatures. And you get higher temperatures when you kind of like compress the whole star into a smaller format. But at some point, you know, when you squeeze atoms and electrons together, you cannot actually exceed this kind of like squeezing beyond a certain point, because the electrons will become degenerate at some point, or the matter will become degenerate. And this electron degeneracy pressure is kind of like the limit value to which we can squeeze a star together. So the answer is that we cannot squeeze it more than that unless we have kind of like the evolution of a neutron star. But also in the case we have also, in the case of a neutron star, we have neutron degeneracy pressure. So same principle, you can squeeze neutrons only to a certain limit, but not any more than that.
All right, thank you. So I think that's it on the YouTube end. Ellie, is there anybody who has tweeted you questions?
I've been refreshing it. I don't see any, so I think we're good.
All right, well, with that, thank you everyone for tonight. This was a lot of fun. It's our first time doing this, so hopefully you guys can join us in December, and we won't have to send out too many extra links there. So thank you viewers for coming here and supporting SPS and supporting Dr. Lewandowska, and thank you, Dr. Lewandowska, for
Thank
doing
you.
this.
Yes, thank you very much.
Yeah,
This was a
she
lot
was
of fun.
actually, yeah, she was actually scheduled to talk back before lockdown happened the first time. So we finally got here to November, but yeah. All right. Well, any other remarks from you guys?
Just thank you again, Natalia. It was super.
It was awesome. Thank you so much for letting me do this. Even in lockdown or almost lockdown again.
Great.
All right. Well, I will see you guys in December.
Thank you. See you guys later.
Okay. Okay. Bye.
Bye.